Good evening and welcome to another Learning Together session sponsored by the Brosis Foundation. This is a great plan that we have to provide additional math experience or exposure for anyone, students or no students, students or parents, anyone who is interested to remind themselves, refresh themselves of math concepts, or even to learn new math concepts. We also have Learning Together sessions in English conducted by Ms. Dawn Dawes. So we have both things going, both math and English. So over the last two sessions, we have been exploring matrices. The first session we defined certain vocabulary associated with matrices. And last time we were together, we work with operations, arithmetic operations that involve matrices, such as addition, subtraction, scalar multiplication, as well as matrix multiplication. Today, we're going to take it a step further as we prepare for a very significant climax, which has to do with how do we use matrices to solve systems of linear equations. So today, we're going to go into what is known as the inverse of a 2x2 matrix. You can also have the inverse of a 3x3 or the inverse of a 4x4. But we're going to start with the 2x2 to just give you an idea of what is involved and how it can be used. Okay? So when we speak of the inverse, what are we talking about? Well, I'll tell you what it stands for. First of all, if I gave you the matrix A, then the inverse, oops, that's not pretty. The inverse matrix is denoted as A to the minus 1. And it is such that if this is a 2x2, then this is going to also be a 2x2 matrix. And A times A to the minus 1 will always be equal to A to the minus 1 times A. And it is always going to be the identity matrix, the 2-2 identity matrix, which is equal to 1, 0, 0, 1. Okay, translation. If matrix A has an inverse, then when you multiply the matrix by its inverse, you get the identity matrix. It's called the multiplicative identity matrix, which has the entries or the elements 1, 0, 0, 1. So within this diagonal, from the top left to the bottom right, you'll have ones and all other entries will be 0. For example, if A was a 3x3, let's use the letter B instead. If B was a 3x3 matrix, then, and B to the negative 1, if that exists, this would also be a 3x3 matrix. When you multiply them, you will get the I3. The I3 matrix, which is a matrix that has 1, 0, 0, 0, 1, 0, 0, 0, 1. Again, if it is the inverse, you will always get the identity matrix. So therefore, the question is, how do we calculate the inverse without just guessing? How do we calculate the inverse? I'm glad to let you know that there is a process, there is a method by which we can calculate the inverse. So now you know that if you calculate an inverse, you can test to see if it's correct. How do you test? By doing the matrix multiplication. Now, the last time we were together, we discovered that matrix multiplication is not commutative. What does that mean? What we discovered is P times Q is not equal to Q times P. In other words, matrix multiplication is not commutative But now I'm going to share with you, except if P and Q are inverses. In other words, if P is the inverse of Q, of course, vice versa, Q will be the inverse of P. Then when you multiply a matrix by its inverse, you will get the same if you flip them around. The order does not matter. Pretty cool. So that's one big thing about inverse matrices. The order does not matter. Okay, good. So, are you interested to see how we do this? Yes. To find the inverse of a 3 by 3 is very complicated. If you want, you could send me a message if you want me to do it. But for now, just by giving you the 2 by 2, it gives you an idea. The 3 by 3 takes up to another level. It will take us maybe 2 sessions to complete that, but it's doable. I teach that all the time. So keep that in mind. If you want it, ask for it. So here we go. So I'm going to explain the steps in an abstract manner, and then afterwards, we go into specifics using numbers. So guess what? Although it's math, I'm going to use letters just to make you excited, make you happy. And then after letters, we'll use numbers. Oh, you're going to say numbers are boring, but that's okay. All right? So here are the steps. If So I'm going to spell the steps out one by one. And if you follow the steps systematically, you will get to your destination. Step 1. Find the determinant. Determinant of A. Okay? So it's abbreviated determinant of A. It's also written as A, B, C, D. So you can write DET for the abbreviation DETA, or you can have the absolute value symbols. Okay? So this is a number, whereas this is a matrix. So notice you have square brackets, or if you have parentheses, that's a matrix. But if you have these vertical lines, the absolute value symbol, then you're looking for the determinant. So it's a symbolic way of referring to the determinant of A. It is equal to, by definition, it's AD minus BC. So it's AD minus BC. That's the determinant. Now, here's a very important point. If the determinant is 0, the inverse matrix does not exist. So if this is equal to 0, there is no inverse. Let me make a note of that. So the converse must be true. If the determinant is 0, there's no inverse. If the determinant is not 0, then there is an inverse matrix. Okay? Good. So that's step 1. Let's go to step 2. As I said before, I'm going through the steps using letters in a generic manner, and then I'm going to go specific. So, step 2, a to the minus 1 is going to be equal to 1 over the determinant of a. You see, 1 divided by the determinant of a. So now you see, if the determinant of a was 0, then this would be invalid. This would be meaningless. This would not be of any use at all. It's undefined. So that's important. So it's 1 over the determinant of a times. And here it is. Notice it's a 2 by 2. But watch what's going to happen. Ready? Here we go. A and D switch places. So D comes here and A goes there. B and C change signs. So this becomes negative B, this becomes negative C. Now this is determinant of A is a number, so it's 1 over that number times each entry. So this is a scalar multiple of this version of the matrix. Okay? And that would be your answer. And I promise you that if you follow those 2 steps, you will get the inverse of matrix A. Okay? And of course, when we get that inverse, we can test to see if it's correct. Because when you multiply the inverse by the original matrix, you should get the identity matrix, the multiplicative identity matrix, which would be, in this case, 1, 0, 0, 1. Okay? Let's go for an example. I'm going to take questions from I'm going to take a matrix from the book. Okay, so let's go with -3, -2, and -1, 1. So what do we have? We have matrix B is a 2 by 2 matrix, and we need to find its inverse. Oh, one thing I didn't mention to you is that every matrix that has an inverse must be a square matrix. In other words, you must have the same number of rows and the same number of columns. So it could be a 2 by 2, a 3 by 3, 4 by 4, n by n. The number of rows must be equal to the number of columns. Got it? So you can only find the inverse of a square matrix. Okay, so what is our first step? Our first step is to find the determinant. That's our first step. Find the determinant of matrix B. So here we go. Determinant of B is equal to AD, so it's 3 times 1 minus BC. What is that equal to? That's equal to 3 times 1 is 3 minus negative 2 times negative 1 is 2. So that gives us a determinant of 1. So now we know the determinant is 1. We can conclude that the inverse matrix b to the minus 1 does exist. Okay, the inverse exists. So yeah, we can go to work. We can go to the next step. Okay, good. And then from here, we know that b to the minus 1 is going to be equal to 1 over the determinant, 1 over the determinant times these two switch places. So this becomes 1, this becomes 3. These two change signs. So this becomes 2, this becomes 1. Of course, this looks ugly. What is 1 divided by 1? It's just 1. And 1 times anything is that thing, it remains unchanged. So therefore, your final answer is 1, 2, 1, 3. Now, I am saying to you that this matrix has an inverse that is equal to that. I also told you how to test if your answer is correct. Do you remember? Yes, you do. Multiply the matrix by its inverse and see if you get the identity, the I2 identity. Okay? Which is going to be 1, 0, 0, 1. So, ready to test? Let's go. Let's see. And remember, we said that the order doesn't matter. Okay? You could put b times b to the minus 1 or b to the minus 1 times b. You will get the same result. Let's go. So b times b minus 1 is going to be equal to 3, negative 2, negative 1, 1 times 1, 2, 1, 3. Now, the last session we discussed matrix multiplication. Remember, it's all about rows times column. A row times a column, a row times a column. That's how we do matrix multiplication. So that was the last session. So if you don't know how to multiply matrices, you have to check the previous session, and that will give you the full practice on that. So now we're just gonna do the work. So let's see if it's gonna work. This is a 2 by 2. This is a 2 by 2. We said that the prerequisite in order for the multiplication to be possible, in order for the product to exist, this number must be equal to this number. So that's where you get your glasses. Those numbers must be identical, and then the product will have these dimensions, this 2 by 2. So we can go ahead and put our 2 by 2. We know we need 4 entries. 2 times 2 gives us 1, 2, 3, 4. Again, last session, I explained how to get the value of this entry, the value of that entry, the value of this entry, and the value of that entry. So now, since we already know how, I'm going to just do it. How do you, this is called the 1, 1 entry. Suppose you want to call it the C. Suppose you call the product. What does it mean? First row, first column. First row, second column. Second row, first column. second row, second column. So it's positional, okay? The elements are positional. So we take the first row, multiply times the first column. We end up with 3 times 1, 3 times 1, plus -2 times 1. What do we get? 3 times 1 is 3. Positive, well, -2 times 1 is -2. So the first entry is uno. Is 1. So now we're going to take the first row and multiply times the second column. The first row, second column. Go. So it's going to be 3 times 2, 3 times 2, plus -2 times 3. What do we get? 3 times 2 is 6. -2 times -3, -6. 0. Now, what position is this? This is the second row, first column. We're going to take the second row times the first column. What do we get? I'm just erasing because I need the space, that's all. Because this would be part of your work if you were showing all the stuff you're doing. So the second row times the first column, so it's going to be -1 times 1 plus 1 times 1. Okay, -1 times 1 plus 1 times 1 equal to -1 plus 1 equal to 0. Now, if you are a betting person and I was to ask you, what do you think the last value going to be? What would be your bet? You're correct, you'd have said 1. Let's go for it and see if we get 1. So, what is it? The 2-2 position, it's in the second row, second column. It's at the intersection of the second row and the second column. So it's going to be the second row times the second column. So it's going to be -1 times 2 plus 1 times 3. -1 times 2, -2. 1 times 3 is 3. -2 plus 3 is 1. Now, I think it's very important that I demonstrate to you that when you multiply a matrix by its inverse or vice versa, the result is the same. So what I'm going to do now is that I'm going to flip these two around. I'm going to write b minus 1 times b, and let's see if we get the same result. Got it? Because I stated it, but I want to prove that it is true. So here we go. Oh, I started to erase. So it is b to the minus 1 times b. B to the minus 1 is 1, 2, 1, 3. Okay, let me bring this up further. So b to the minus 1 times b is going to be equal to 1, 2, 1, 3 times b is 3, -2, -1, 1. Like I said, in our previous session, we did demonstrate that A times B is not necessarily equal to B times A. We proved that it's not commutative. And today, you're learning that that happens if the two matrices are inverse of each other, okay? Now we're going to find out. This is a 2 by 2. This is a 2 by 2. So we will get a 2 by 2. Okay? Good. So the first entry is the C11. Again, those labels are just for the positions. We're just trying to identify the positions. Okay, so the first position is the 1, first row, first column. It's going to be 1 times 3 plus 2 times -1. 1 times 3 plus 2 times -1. What do we get? 1 times 3 is 3. 2 times -1 is -2. We get 1. Good start. Let's try the next one. So this is the 1, 2. So it's the first row, second column. So it's 1 times -2 plus 2 times 1. What is that? -2 plus 2 equal to 0. Now we go to the second row, first column. Second row, first column. It's going to be 1 times 3, 1 times 3 plus 3 times -1 equal to 3 minus 3 equal to 0. And finally, second row times the second column, second row, second column. So it's 1 times -2 plus 3 times 1 equal to -2 plus 3 equal to 1. Again, the I2 or the multiplicative identity matrix, the I2. Okay, so that was our first example. Let's try another example. Again, we tested our result to make a point, to prove a point. So once you're comfortable that it works or you understand the process works, you don't have to test every time. But if you're a good student and you want to make sure you're correct, it's a good idea to test, to just check to see if you're correct. Okay. So let's try another one. Let's try 3, 1, 4, 2. So given A equal to 3, 1, 4, 2. Find the inverse matrix. So that's 3, 1, 4, 2. So let's go. First step is determinant of A. Okay? So determinant of A gives you 3 times, notice A times D minus B times C. It's going to be 326 minus 4 equal to 2. So we got a determinant of 2. What does that mean? It means that the inverse does exist. Okay? So now we're ready to go to work. Okay? So A minus 1 is going to be equal to 1 over the determinant. So it's 1 over 2 times, and in this case, 2 and 3 switch places. 1 and 4 change signs. So your final result is going to be a half times 2 is 1, negative a half, negative 2, and 3 over 2. All I did was did the scalar multiple. I took the half and multiplied every entry by a half. Half times 2, 1. Half times negative 1, negative a half. Half times negative 2, ooh. Sorry, a half times 4. A half times negative 4 is negative 2. And a half times 3 is 3 over 2. So, do you think this is correct? Your answer is yes. And if I say prove it, how would you prove it? You would take this, multiply times that, and what should you get? You should get the I2 matrix, 1, 0, 0, 1. Let's go for it, let's check. So we're gonna go A times A to the minus 1 is going to be equal to 3, 1, 4, 2 times 1, negative a half, negative 2, so far so good. So we know that it's a 2 by 2 times a 2 by 2. The result is going to be a 2 by 2. Okay? And now we're ready to find what the result is going to be. So this is a 1, 1 entry. So it's the first row, first column. So we end up with 3 times 1 plus 1 times negative 2. That's going to give you 3 minus 2 equal to 1. Great start. Great start. I love it when that happens. Okay? Let's go to the 1, 2 entry. First row, second column. First row, second column. It's going to be 3 times negative a half plus 1 times 3 over 2. So what do we get? 3 times negative a half is 3 over 1 times negative 1 over 2. You multiply the top, you multiply the bottom. So the answer becomes negative 3 over 2 plus 3 over 2. And that gives me 0. Okay? 2 down, 2 to go. So now we're going to go to the second row, first column. Second row, first column. So it's 4 times 1 plus 2 times negative 2. Okay? 4 times 1 is 4. 2 times negative 2 is negative 4. Result is 0. And then finally, we end up with the second row, second column. Second row, second column. Second row, second column. So it's going to be 4 times negative a half plus 2 times 3/2. What is 4 times negative a half? The answer is 4 times negative a half is -2. And what is 2 times 3/2? It's 6/2, which is 3. And -2 plus 3 is 1. So we have just found a way to find the inverse of a 2 by 2. We also know a way to test if it's correct. So the only thing we have left to do is to be able to check to see how we can use a 2 by 2 matrix to solve a system of equation. So let's go for it. Use matrices to solve. Okay, so here's what we have. We have 2 linear equations, and they're asking us to use matrices to solve this system of equations. Okay, so here's how we do it. The first step is to rewrite this as a matrix equation. So you have a linear equation, you rewrite it as a matrix equation. And the way you rewrite it is, you take the coefficients 3, -1, 1, -2, put them in one matrix. You take the variables x and y, put them in another matrix. And you take the constants 11 and 2, put them in another matrix. So here we go. It's going to be 3, -1, 1, -2, times x, y equal to 11, 2. This is called a matrix equation. Okay, that's called a matrix equation. So we went from a system of linear equations to a matrix equation. This is a 2 by 2. This is a 2 by 1. 2 rows, 1, 2, 1 column. And if you notice, this is identical to this. And then the result is a 2 by 1. 2 by 1. So it makes a lot of sense. Let's check. 3 times x is 3x. Plus -1 times y gives you -y. And that's going to give you the first position. Second position, this is the second row, first column. Second row, first column. 1 times x is x. Plus -2 times y, -2y. Equal to 2. So it is consistent with what we understand. So now, what do we need to do? we need to get x, y by itself. So we need to get rid of this 2 by 2. Now, if you remember in our last session, we said that we could add matrices, we could subtract matrices, and in some cases we could multiply matrices. Remember, we discussed that there are certain conditions, there is a condition that must be satisfied in order for two matrices to be able to be multiplied. Okay, that was covered in the previous session. But we said also that matrix division does not exist. Now, normally, if you have an equation, where, for example, if you have 4p equal to 20, you can get p by itself by dividing by 4, dividing by 4. And you end up with p equal to 5. So here, to get rid of this matrix, if we could divide, then that we would have been able to get rid of that. But then when we come over here, this divided by a 2 by 2 matrix is like, doesn't exist. It's meaningless. So what is a different way to get rid of this matrix? I'm so glad you asked. The way you do that is you multiply both sides by the inverse of this matrix. By multiplying by the inverse of this matrix, we get rid of this and we end up with xy by itself. So let's go for it. I promise you, let me show you what I'm saying. If I put the inverse here, the inverse times this gives me 1, 0, and 0, 1. Let's watch this. 1, 0, 0, 1 times x, y. I am trying to tell you that this is going to give us x, y. It will be unchanged. Watch. This is a 2 by 2. This is a 2 by 1. So therefore, the product exists, and therefore this is a 2 by 1. So this is number 1 entry, obtained by the first row, first column. This is the next entry, second row, first column. So here we go. 1 times x is x, 0 times y is 0. So we just get x. Come to this one, 0 times x is 0, 1 times y is y. So what's the conclusion? If the inverse exists, when I multiply the inverse matrix times this, it cancels that portion. But I also have to multiply the other side by the inverse matrix. Got it? Yes. So here we go. So xy is going to be equal to 3, negative 1, 1, negative 2 to the minus 1. Remember I told you to use the negative 1, the power, the exponent negative 1 to refer to the inverse matrix. Okay? So now we need to find this portion here. But we have a cute trick as to how to set this up so it flows nicely. Watch this carefully. To the side, we find the determinant. So the determinant of 3, negative 1, 1, negative 2. Remember, the absolute value symbol gives you the determinant. So 3 times negative 2 minus negative 1 times 1. So this times this minus this times that. So we end up with negative 6, then minus negative 1 plus 1 gives us negative 5. So that's the determinant. So therefore, for this, it's going to be 1 over negative 5 times This comes here, this comes here. So it's negative 2 and 3. This becomes 1, this becomes negative 1. And then you have 11 and 2. So here's a tip. If you were to multiply by the negative 1/5, you're gonna have a lot of ugly fractions. So don't do that. Keep this fraction for the very end. Go ahead and multiply this 2 by 2 by this 2 by 1. And whatever you get at the end, you do the scalar multiplication. So it's going to be equal to negative 1/5. This is a 2 by 2. This is a 2 by 1. So we're going to get a 2 by 1. And what are the values that will go here and here? Ready? Negative 2 times 11 plus 1 times 2. So I need some space. So it's negative 2 times 11 plus 1 times 2. What is that going to be? Negative 22 plus 2 equals to negative 20. This entry here is the second row, first column. So it's going to be negative 1 times 11 plus 3 times 2 equals to negative 11 plus 6 equals to negative 5. So now we're ready to do the scalar multiplication. It's negative 1/5 times each entry in our 2 by 2 matrix. What do we end up with? Negative 1/5 times negative 20. Negative 1/5 times negative 5. So what are we learning? We're learning that xy is equal to 4, 1. What does that mean? It means that x is 4 and y is 1. So now I ask you the question, how can I check if my answers are correct? How can I check if x is 4 and y equal 1 are the solutions? I'm so glad you asked. Why not go straight back to the original equations, plug in for x and y, and see if we get 11 for the first one, see if we get positive 2 for the second one. If we do, we know we're in the money. Okay, here we go. And x is 4. Let me make some space because we need some room. So we end up with x being 4, y is 1, so it's 3 times 4 minus 1. 3 times 4 is 12 minus 1 equal to 11. Whoa! The first equation works perfectly, but we're not over yet. It has the solutions have to work for both equations. And if there were 3 equations, you would end up with 3 values. All 3 equations would have to be satisfied correctly in order for you to celebrate. So now we're going to go to the second equation. What do we have? X is 4 minus 2 times y, which is 1. So now we have 4 minus 2 equal to 2. Oh, wonderful. The second equation works out to be 2. So therefore, using x as 4 and using y as 1, perfect. Okay, let's try a second example. Okay, let me check to make sure that the numbers work properly. Yes, let's do it. 5a plus 4b equal to 13. Negative 3a minus 2b equal to negative 8. Okay, let's see what happens. Okay, first step is to write the matrix equation. So it's going to be 5, 4, negative 3, negative 2 times a, b. Is that equal to 13? Based on our discussion, the way to get rid of this 2 by 2 is to multiply both sides by the inverse of this 2 by 2. But we are putting the inverse to the front. So we have to put it to the front so that we're consistent. So therefore, a, b is going to be equal to the inverse matrix of 5, 4, negative 3, negative 2 times 13, negative 8. And that's going to give us, we'll see, let's go. What do we do as our first step? First step is to find the determinant of this 2 by 2. So we go. Five times negative 2 minus 4 times negative 3. Okay. 5 times negative 2 minus 4 times negative 3. What do we end up with? 5 times negative 2 is negative 10. Negative 4 times negative 3 is plus 12, which gives me positive 2. So according to the routine, it's going to be 1 over the determinant. So it's going to be 1 over 2 times these two change positions and these two change signs. So negative 2 goes here, 5 goes there. Change the signs, negative 4, positive 3. And then of course we have 13 and negative 8. The advice I gave you was save the 1/5 for last. Do not distribute the 1/5, otherwise you're gonna have ugly numbers to work with. It would still work, but it will give you a headache. We don't need no headache, okay? So we'll save the half, we'll go ahead and multiply these whole numbers, and then at the very end, we multiply by a half. So what do we have? We have a half times, this is a 2 by 2, this is a 2 by 1, we end up with a 2 by 1. Okay? And now we're ready to work. So it's going to be this times this gives me the first entry. Then this times this gives me the second entry. Okay? So here we go. It's going to be negative 2 times 13 plus negative 4 times negative 8. It's equal to negative 2 times 13 is negative 26 plus negative 4 times negative 8 is positive 32. That to me is going to be 6. Positive 6. Now, we're going to go to the second row, first column. So it's 3 times 13 plus 5 times negative 8. Okay, what do we get? 3 times 13 is 39. 5 times negative 8 is negative 40. So that gives me negative 1. With the distribution, what is a half times 6? It gives me 3. What's a half times negative 1? It gives me negative a half. So what are my answers? My answers are A equal to 3, B equal to negative a half. And of course, as a good student, we want to check to make sure that our two answers work perfectly for both equations. Okay? Pretty interesting, right? Completely different level of mathematics here. Matrices, okay? Completely different level. Okay, so I'm gonna need some space to check if it's correct. Okay, so A is equal to 3, B is equal to negative a half. So 5, so we're checking. 5 times 3 plus 4 times negative a half. What is that equal to? It's going to be equal to 15. 4 times negative a half is negative 2, equal to 13. 13 is correct. Let's go to the next one. Negative 3 times A, which is 3, minus 2 times B, which is negative a half. It's going to be equal to negative 3 times 3, negative 9. Negative 2 times negative a half is positive 1. Negative 9 plus 1, negative 8. Negative 8 is right there. Wow. We have just discovered that, well, back in the days when we did systems of linear equations, we had substitution and we had elimination. Substitution and elimination. And now we have just added to this the inverse matrix. So now we have 3 methods of solving systems of equations. And of course, we have the old-fashioned graphing, where you draw the 2 lines and see where the 2 lines intersect. And the point of intersection would be the x value and the y value of your solution. So that would make it 4 solutions, 4 options right there. And of course, there's one other method known as Cramer's rule. Cramer's rule. So maybe next time we're together, we could touch Cramer's rule. And then we could do, maybe I might introduce you to how, just give you an idea, what it would take to find the inverse of a 3 by 3. So that's going to be a step up. But why not? You know, you have been very calm over the last 3 sessions. Maybe it's time for me to take you to another level. So I'll do Cramer's rule and then pop in how to find the inverse of a 3 by 3. Is that good? Okay. This was another Learning Together session sponsored by the Brosis Foundation. We do trust and hope that you found this interesting, helpful, and that you tell a friend or tell a family member. Let them know that these resources are available both in math and English. Spread the word because it's free, and the purpose of this is to help students all over the world to have additional help where they need it, especially in math and English. Again, on behalf of the Brosis Foundation, we thank you for spending this time together with us, and we trust that you'll enjoy the rest of your day.